Okay, hello. So today we are just continuing the last part which is left in the liquid extraction, and if you remember, we were discussing the number of theoretical stages, how to estimate it. I had already told you that this particular estimation is based on a graphical procedure. You can do the graphical procedure either on a rectangular plot or on a ternary plot. I was discussing it on a rectangular plot, and I will be continuing the discussion today on the rectangular plot as well. And you must have realized by this time that the entire graphical construction, it is based on location of 2 points, the mixture point and the difference point. The mixture point gives you the total mixture, the location, or rather the where the mixture is located inside the immiscible dome. And the so therefore, and the next thing was, just a minute, and the next thing was the location of the delta point, the difference point, which gives you the net result, or rather which gives you the, just 1 minute, which gives you the net outflow from any particular stage, starting from stage 1 to the last stage n. It gives you the net outflow from any particular stage, maybe stage 1, stage 2, stage 3, etc. So therefore, all lines which locate the streams coming out from any particular stage has to cross through this particular point. Similarly, E1F has to come here, and in the same way your SRN, it also has to come here. So, and in the same way your E2 R2 has to come here. So, therefore, I had described the construction as, initially we draw Fs, we draw Rn and E1, and then from Fs, if you know the total amount of solvent, you know M. Once you know M, you know Rn, so therefore, you can locate E1. Then you can join Fe1 and you can join SRN, you locate the delta point. Once the delta point is located, then you know that all the E1, R2, E3, sorry, E1, R1, E2, R3, E4, all these things, they should go through this particular delta point. So, once you have located this delta, the next step was that from E1 you drop a tie line, you get R2. Then from delta you draw R2 and extend it, you get E2. From E2 you draw a tie line, you get, I am sorry, this was R1, very sorry, R1. Then from E1 you draw a tie line, you get R1. From delta you draw the difference line, you get E2. From E2 you draw a tie line, you get R2. From R2 again from delta R2, if you draw and to extend it, you are going to get E3. Again from E3 you can draw a tie line, you can continue this until you reach this particular composition. Now, there is just one thing here which needs to be remembered, how to construct tie lines. This is one other thing that you should be doing. Now, for constructing tie lines, what we can do, there are different ways by which you can construct tie lines. The easiest thing from a graphical construction which I felt was that just beside this particular rectangular plot, you can draw a two-dimensional plot of the mole fraction of the mole fraction of the solute in the extract phase, mole fraction of the solute in the raffinate phase. So, therefore, this is raffinate phase mole fraction of solute, this is extract phase mole fraction of solute. Perfect. By this you can generate this particular equilibrium curve. Now, in this equilibrium curve, this E1 R1 should lie here. So, what we do, from E1 you draw a straight line here, right. So, this gives you the point of XB and YB which are in equilibrium to one another. From here you drop a straight line, and then so therefore, this straight line also gives you the xb, which is in equilibrium with the, rather this also gives you the xb, sorry, which is in equilibrium with the, with this yb star. From here you draw a straight line, then you can locate the point of tie line here. So, this is the process by which we locate the tie lines. So, therefore, now to summarize the entire process, what we do, again I repeat, you have located the M point, you have located the delta point, and then from E1 you will be drawing the tie line. You simply, you have already drawn the equilibrium curve. From E1 you come here, drop down, go straight, you have located R1. Then delta R1 extend to go to E2. From E2 again draw a straight line, drop down to the XB, the diagonal line, extend it straight, you get the point R2. From delta R2 and then extend it, you get E3. Again from E3 come straight here, and you locate this particular point, drop down straight, go back, you get R3. Again delta R3 extend, you get E4. So, therefore, this is the entire process by which the number of theoretical stages are constructed. It is important for you to remember that although it appears complex, it is not so. It is just based on location of the mixture point and location of the delta point and the location of the tie lines, these three things. First you are going to locate the mixture point, after that you are going to locate the delta point, and then the location of tie line, if you are doing it in this particular way, it is not at all difficult. You can locate, and in this way the number of steps has to be continued till you reach the final concentration of the solute in the raffinate phase. Well, so this gives you the entire construction. Now, there is one thing left. Normally, when you are given a problem, you are specified the feed flow rate, you are specified the feed composition, and you are also specified the final solute composition in the raffinate. And as I have told you that this is usually specified in the after the solvent recovery. So, therefore, to locate the point on the ternary plot, you need to join this R with S, and then the point where it meets the raffinate curve gives you the actual Rn. So, normally these are the three things that you are given, and you are asked to start with this feed composition, feed flow rate, and arrive at this solute composition in the raffinate. First what you do, you select the solvent, and after you select the solvent, you generate the equilibrium data. So, therefore, you are in a position to draw this curve, you are in a position to draw the ternary plot. Now, the important thing is how much solvent are you going to use. You know very well that the more amount of solvent you are going to use, M keeps on shifting towards the S. Now, definitely you would like to do this particular separation by using the minimum permissible amount of solvent. How are you going to decide that? If you remember in absorption what you had discussed that the point where the operating line and the equilibrium curve they touch each other, that gives you the minimum solvent. Then accordingly you select 1.52 or 1.3 times the minimum solvent and to start working. Same concept applies here as well. In this case also, can you tell me what is going to define the minimum solvent? The minimum solvent, if you think, it is going to be decided, say from delta, if you have located delta in this particular way, sorry, this Rn En plus 1, wait, it has become slightly clumsy, very sorry. Yeah. So, therefore, if suppose you are having a E1 here. So, therefore, if from here and from En R prime, if you are joining, you are going to get delta. Now, one thing you remember, suppose from delta to F, the line which you have which is there, which you are going to extend to find out E1, if that coincides with a tie line, then what you get? You cannot go below that. That is the minimum that you are going to get. So, therefore, in order to locate the minimum amount of solvent, what you need to do, you need to locate the E1 corresponding to the minimum solvent. How can you locate that? You have to locate F, then corresponding to F you have to locate the tie line which passes through F, or the tie line which corresponds, or rather which is an extension of delta F. Once this particular you can locate this, location of tie line is the same, you will have a equilibrium curve here, from there you are supposed to locate. Once you find out that the tie line from delta F, that becomes the tie line, you extend the tie line, then the point where the tie line it intersects with the extract curve, that gives you E1 minimum. Once E1 minimum is located, then in that case F and S are already joined. In order to locate M minimum, you need to join Rn and E1 minimum. This gives you, once you have done it, you can find out the M minimum point. Once M minimum point is located, you can find out this length, you can find out this length. You know that this by this gives you S by F. So, from there you are in a position to find out the minimum amount of solvent that you can use. Now, the other way around, can you tell me what is the maximum amount of solvent that can be utilized to bring about the same separation? If you keep on increasing the amount of solvent, M keeps on shifting. M can keep on shifting till M touches this particular point in the extract curve. After that, if you add more amount of solvent, naturally you enter the zone of miscibility, and as a result we cannot perform extraction. So, the maximum amount of solvent corresponds to M lying on the extract curve, and the minimum number corresponds to the M which can be located corresponding to the E1 minimum. Normally what we do? We find out M minimum, and then corresponding to the, from M minimum we find out S by F minimum by the lengths as I have shown you. Once you have located R minimum, you have to find out R which lies between R minimum and R maximum corresponding to M maximum which lies on the extract curve. Usually then the actual amount of solvent that we take, that lies, or that is around 1.1 to 2 times of the R minimum, or the solvent corresponding to the minimum point. So, therefore, before you start the problem, you have to decide the total amount of solvent. In order to decide the total amount of solvent, before you have done anything, you know this point, you know this point, you know this or this, any one of them depending upon the specification of the solvent. First thing what you need to do is to locate this point. Once you have located this point, you are in a position to find R minimum. Once you have found R minimum, you can find out S minimum. Then you take say about twice or 1.1 times, definitely we will like to start with 1.2, 1.3. If we get more or less optimum number of stages, we will proceed, or else we will slightly increase the amount of solvent. Once we have increased the amount of solvent, then we locate the M point. Moment the M point has been located, we can locate the E1 point. Once the E1 point is located, then using FE1 and this, we locate the difference point, and then we draw the xy equilibrium curve on the left hand side, start locating tie lines and start doing the construction accordingly. So, I have given a particular design problem here for you to try, where we need to recover acetone from 1000 kg per hour of an aqueous stream which contains 40%. So, therefore, XBF equals to 0.4, and we would like to go for XBRN equals to 0.05. Remember one thing, this is the this refers to the prime after solvent recovery, this is the amount of solvent that is there. So, therefore, this 5% acetone, it lies somewhere here at 0.05 curve. This is what. So, from here if you join S, you will actually get the Rn prime Rn point. This refers to the Rn prime point. So, the problem is just as it is, that acetone is there and we would like to recover acetone from a 1000 kg per hour aqueous stream, which contains 40% weight per weight acetone, and we would like to have something which has 5% acetone after solvent recovery. First thing, if you remember the way we had done, we have to choose the solvent. Now, the most common solvent which is there in this particular case is the MIBK. Okay. So, therefore, the first thing we would like to do is to start with MIBK. Now, we had obtained the equilibrium data for MIBK, and this is the curve which this is the rectangular plot corresponding to MIBK. Now, once we constructed this, what we noticed is that the plate point, if you observe here, that is very close to 0.4, which corresponds to the feed composition. So, therefore, the closer we go to the feed composition, we know that we cannot perform extraction. So, therefore, although MIBK was the preferred solvent, we could not opt for MIBK. The next choice that we had, we selected the chloroform phase. From the chloroform, the data is there, we plotted it, we found the plate point to lie around 0.575, which is quite far away from 0.4. And moreover, we found that chloroform has, if you observe the data, you find chloroform has a very less miscibility with water. So, therefore, we can assume the solvent point to start from here. And also we found that acetone, it is completely miscible with both the phases. So, we had proceeded with chloroform as the extraction solvent, and more or less just the way the process that I had told you, in the same particular way we had proceeded in this particular case, and we had found out S minimum, and then from there initially we had started with 1.3, you can try it out for yourself. We got a large number of stages. So, therefore, just to bring it down, we increased the total amount of solvent to about 1.75 times. In other words, K was the K was taken as 1.75, and then the calculation was repeated, and we got a reasonable about 5 to 6 number of theoretical stages. You can try it out for yourself, and you can see that at the end what you are getting. Right, just the same way, locate M minimum, then locate M, then locate the delta point, then drop the tie lines. The entire thing is shown in this particular figure. And just for your convenience, I have just jotted down the steps in sequences which you need to follow. Please do not follow anything blindly. Try to understand that the whole construction rests on locating the mixture point and the delta point and the construction of tie lines. So, the entire thing has been written down here just for your convenience. You can follow this and you can complete, or you can find out the number of theoretical stages in this particular case, right. The entire thing has been written here. Now, this is the conventional approach that you use, but under certain cases where the feed and the solvent, they are completely immiscible with one another, and under that case, suppose you can express the solute concentration as weight ratio. What is weight ratio? If you remember, this capital X is the weight fraction by 1 minus x, and the same way y equals to y minus 1 by y. So, in this particular case, if f prime and s prime, they are constant in all stages, when it will happen? When both of them are perfectly immiscible. Then under that case, we find that the situation becomes similar to stripping, which you have learned. Under that conditions, we will be getting a linear operating curve whose equation will be given by f prime by s prime or by E prime by R prime, right. Now, you can very well get it done, or rather you can understand it if you can perform a mass balance from the feed stage to any particular stage n. Same thing can be obtained if you start from the raffinate end and come to the stage end. I have written down the mass balances for the two cases. You will find that it is completely identical to the thing that you have done for your absorption and stripping case. Only in those particular cases the nomenclatures have been changed to E prime and R prime in this particular case. Accordingly, Y, E and X R, they denote the composition of the solute in the extract and the raffinate phase. Just the nomenclatures are changed, otherwise everything is completely same. So, therefore, under this particular condition we find that when you get when the feed as well as the solvent, they are completely immiscible with one another, and under that condition when you are expressing the operating line in terms of weight ratios or mole ratios, whatever is convenient for you, under that condition we get a linear operating line and a curved equilibrium line. If you find here, you can locate the endpoints, you can locate x, b, r, n, which is the point here, and this refers to the inlet condition. So, the 2 points are located, it can be joined by a straight line, and just the way it was explained in absorption, you can find out the number of stages in this particular case. The procedure, the concepts are completely similar to what was told to you during absorption. To be honest, this is similar to the stripping operation, you have to keep in mind, and that is why the operating line is below the equilibrium curve. You will remember that if for absorption, the operating line is above the equilibrium curve. Now, the other thing is when both the operating line and the equilibrium curve, they are linear, and the equilibrium curve has a slope of m. This was also discussed during absorption, and you were told that under that condition n can be obtained very easily from the Kremser equation. In fact, if you remember, we have used Kremser equation for solving the mixer settler problem, because there also we found that more or less the equilibrium and the operating line over the range of operation that we were performing, they were practically linear, and the two phases, they were completely immiscible with one another. So, therefore, the same equation that was told to you during your absorption stripping class, the same equation you can use here in order to find out the number of theoretical stages when the operating line and the equilibrium curve, they are linear to one another. The only thing is, in absorption you had used the absorption factor, which was equal to L by mg, and in this particular case it is the extraction factor, it is equals to ml by g. There we had used, in this particular case it is the slope of the equilibrium line and the operating line, we call it the extraction factor, and there it was called as the absorption factor. Otherwise, the expression is completely the same. If you are fortunate enough that you can get a linear operating and equilibrium curve, then once you calculate NTS in this way, in whatever way you calculate NTS, finally the column height is given as a product of NTS and the HETP. This HETP, as you will see, that more or less for extractors in packed columns, sieve plates, even for agitated contactors, more or less data on HETP is available from experience, and you can use, there is a range of data available for HETP, you can use any particular point within that particular range, and you can get an idea regarding the column height. Well, so therefore, once the column height has been decided, the next thing is estimation of column diameter. Again, I will go back to your column internals that you have studied, and under that condition, when you are studying vapor liquid, gas liquid contacting, how did we find out the column diameter? I had told you in the beginning of the last class itself that it was basically on the basis of flooding velocity, and we considered the vapor flooding velocity, because under flooding what happens, the vapor velocity is high, and as it flows up, it entrains a good amount of liquid, and due to this particular liquid entrainment, flooding occurs. So, therefore, the vapor velocity is considered, and the vapor mass flux or the vapor volumetric flux is considered, and accordingly the diameter is found out. Now, here there is something that you need to keep in mind. The point is that in extractors, flooding can occur in a slightly different way. While in gas liquid vapor liquid contactors, flooding occurs just by increase of vapor velocity. In this particular case, definitely if you increase the velocity of the continuous phase, you are going to get flooding. It goes without saying. Moment you increase the velocity of the continuous phase, quite naturally what happens? It starts entraining the dispersed phase and takes it out, similar to what had happened in vapor liquid contactors. But there is one other thing. Instead of increasing the velocity of the continuous phase, if you increase the velocity of the dispersed phase, what do you get? There is a phenomenon known as phase inversion, which is unique to liquid-liquid systems. It does not happen for gas-liquid systems. During inversion, what happens? If you keep on increasing the velocity of the dispersed phase, at one particular time you will find that the dispersed phase becomes the continuous phase. So, therefore, if you keep on increasing the velocity of the dispersed phase, you find that the dispersed phase becomes the continuous phase and then it starts flooding, because the initial continuous phase has now become the dispersed phase. So, therefore, in this particular case, flooding can occur both by increase of the flow rate of the dispersed phase as well as by increase of the flow rate of the continuous phase. And therefore, when you are going to calculate the total flooding velocity, in order to calculate the tower cross section, you need to take the total mixture velocity into account, because flooding can occur by increase of not only UC, but also by increase of UD. And you also need to remember that whenever there are some contaminants at the interface, that can cause phase inversion by interface destabilization, and that can also cause flooding. Now, how do you understand that flooding has occurred? The interesting part is, as I had initially told you, that when you have such a column where the heavier phase is coming in here, going out here, maybe the lighter phase is coming in, going out. So, therefore, if the lighter phase is the dispersed phase, you have an interface at the top. Now, moment flooding is there, a second interface starts appearing, and moment the second interface appears, you know that flooding has occurred. Well, so to come back to the column diameter, so the column diameter is estimated by the flooding velocity, which is the total mixture velocity, and since from all this you have understood that there are a lot of uncertainties in predicting the flooding velocity. So, therefore, extraction columns, they are usually designed to operate at 50% flooding velocity, it can be lower flooding velocity as well. Well, so after this I do not have much to say. There are certain parameters which I have put down specifically for packed tower design. Here we see that we can use, as I have told you, both random and structured packings. It is important for you to remember that with structured packings the throughput is higher, the turn down is higher, yet in industries the random packings are preferred because they are cheaper and they are easier to clean. And when we select packing materials, it is important to consider the corrosion, and it is important, it is desirable that the packing material is wetted by the continuous phase and it has got sufficient strength. Considering that, ceramic is usually not adopted, because if it is quite brittle and if it breaks down, there is a chance that it is going to clog the pipelines, etc. But of course, at the same time, when aqueous phase is continuous, we often select ceramic for corrosive liquids. Even for water continuous phase, this is cheaper, we can use stoneware and metal packings. For when the organic phase is continuous, we use carbon rings or saddles. There is one very important thing that I would like to mention. When you were discussing gas liquid, vapor liquid contacting, if you remember, the packing surface provided the interfacial area or the area for mass transfer. So, therefore, A was important. In this particular case, you know that the mass transfer occurs around the droplet surface. So, therefore, the packing surface is does not influence the mass transfer, or the mass transfer area is almost independent of the packing surface. It is a function of the dispersed phase hold up, because around the droplets mass transfer occurs. Packing is kept just to increase the turbulence and to redisperse the coreless drops. So, these things I will be skipping. These are just the equation to predict liquid flooding. I will not be covering these things. In case you need this later, all the details are provided in the slide, that the way you are supposed to find out the flooding velocities based on these diameters. I will not be going into the details of all this. And for the sieve tray design also, I have just noted down a few design parameters etc. In case you are interested, you can take it up. One thing I was thinking, the initial problem that was given, if you are at all interested, you can just, after you have found the number of theoretical stages, you have optimized everything, you can just try it out considering a packed bed and using these particular equations, and you can see what you are getting for yourself. For the time being, as far as I am concerned, it is important that you have known the things that I have covered, which will be important for your assessment, is considerations for the choice of solvent, and then how to select the dispersed and the continuous phase, how to find out the number of theoretical stages, how to estimate the column diameter, and the important part is, for column diameter, the total flooding velocity is important, and certain considerations in deciding the packed tower materials etc. And also you need to remember that for the sieve trays, normally we do not use any weir here. This is something which is different from the vapor liquid contactors. The tray spacing, the active area and the downcomer area, the ratios are also different from vapor liquid contacting devices. So, these are the few things that you need to remember, and in any case, if you need any further clarification, you can get back to us. We are going to clarify the doubts. I will also give you a small hint, the particular portions which are important for assessments are marked in red font in all the slides, so that you can just keep that in mind while you are preparing for the assessment. Thank you so much.